All right, so chapter 26. So we start out with electric potential energy. Every conservative force has a potential energy formula. No exception. Electric field, or sorry, back up. The electric force is a conservative force. Conservative forces have a potential energy formula, going back the other direction. And so we need to figure out what is the formula for electric potential energy. I know that the conservative work is equal to the negative change in potential energy. Established under the work energy relationships, the physics 251 kind of thing. And when this came up before, there was a lot of fuzzy minds, I believe. It's my recollection. I have posted a number of videos from 251 under the review category, under coursework review. And so there's a number of older videos just sort of going over some of this stuff. I know conservative work is created by a conservative force. So that's the integral of the conservative force dot drx, whatever letter you happen to be using, but I'm going to use R in this particular case. And that is conservative. The definition of work is F dot D, whatever you're using for position. And then potential energy, this becomes negative of the final potential energy minus the initial potential energy. So I imagine I have some charge here, Q, and I am taking another charge, we call that Q1. I'm taking charge Q2 here from some position of some initial distance to some final distance. And I want to know what is the conservative work being done on charge 2 as I move it from here to here. Well, I have two charges. What's the force between them?
KQ1, Q2 over R squared. R.
Q1, Q2 over R squared. R hat dot dr. So dr hat is basically in the radial direction itself, so this becomes dr r hat, and that's equal to negative u final plus u initial. So the dot product cares about parallel, and my force acting on Q2 is in the same direction as my radial vector, or the same direction as dr. And so this just becomes a simple, well, K, those are constants, so K Q1, Q2, 1 over R squared dr, and that's going to be equal to negative U final plus U initial. I have an integral here in terms of a single variable, so I can do limits of integration relatively simply. And so it goes from R initial to R final. So what's the integral of 1 over R squared dr?
Negative 1 over R.
So I got negative K Q1 Q2 1 over R, from R initial to R final, which is negative K Q1 Q2 over R final, plus or minus the negative K Q1 Q2 over R initial. Therefore, what is a formula for U that would satisfy this, because this is what we got from finding the work, and this is what we got because of the work-energy relationships. They better be equal to each other. So what formula for U would satisfy this?
E equals E.
Is it E? V?
I'm getting confused. I got a lot of letters going through my head right now.
It's just K Q1 Q2 over R.
Does that work? If U is equal to KQ1, Q2 over R, then would that be U final and would that be a U initial? Because I got negative U final plus U initial, so I got negative this right here plus that. I think you were overthinking it, Joseph.
Yeah.
And this K right here is Coulomb's constant, so properly there should be a subscript, but I've been leaving it off quite a bit. Because you know what I mean. What is another value or another formula for U that would also work? Question has stumped many a person.
Just force times radius. I get the same thing.
Oh, throw a 2 in front?
No, just the force times the radius.
Oh. Plus force times.
Or distance moved.
Are you doing it top right there? We do it plus F dot R, that's what you're going for?
I think so, yeah. Oh, was the answer you're looking for just plus a constant?
Yeah, it's just plus a constant. So what that actually, no, because force is not a constant there, so no, that would not work. But plus a constant. Because again, the formula, the work energy relationship tells us what the change in potential energy is. It doesn't actually tell us what the potential energy is. So once you get it down to here, just like in the past, once you get it to here, you just are trying to find a formula that works. But this plus constant allows us to establish where the potential energy is 0 wherever we want. And that was a question I asked on a test years ago, where I asked, I think I had it justify that the potential energy at the surface, or the potential energy at this particular point where this charge is like 3 joules. And the trick came, and the trick was, you can define wherever 0 is, so you can just define 0 side of that, it works that way. Because it's the change of potential energy that's more important. Now traditionally, the constant is 0, and so that means potential energy is 0 when R is infinitely far, or infinitely large, when you're an infinite distance away. But it doesn't have to be. So let's just do a nice little problem here. I do want to also point out, we are dealing with a scalar, which is very convenient. So first let's establish that U sub E equals 0 when R is equal to infinity. I have done tests where I have not written that, and I've given the system and I say, what's the potential energy here? And the really quick answer is, I'm going to define that to be 0. So I try to throw that in there just so that there is more than one answer. Oh, so that there's only one answer. And so if I've got a 4 nanocoulomb charge there, negative 3 nanocoulomb charge there, and a 5 nanocoulomb charge there, we'll make this 0.4 meters. Let's do numbers I'm not using already. 0.8 meters, 0.2 meters, and 0.7 meters. Yeah, it's possible. What is the potential energy of the system? from a philosophical point of view, you start out with one of the charges there. And then you bring another charge from an infinite distance away to where it is currently there. And so it's how much energy does it take to actually move that charge to where it is? And then how much energy does it take to bring the last charge to where it is? Or, given that, my electric potential energy, I have three different pairs. Because my potential energy formula deals with two charges at a time. And so, if I have the potential energy of that, plus the potential energy of that, plus the potential energy of that. So K, so the times 4 nanocoulombs times 5 nanocoulombs over 0.8 plus K sub E 4 nanocoulombs times negative 3 nanocoulombs over 0.2 plus Ke 5 nanocoulombs times negative 3 nanocoulombs over 0.7. The negative sign is important here. It is not telling us direction, but it is actually telling us energy. And there are sometimes, probably more have to do it for 152 than 252, but I set up the problem, I say, just give me the equation, you don't actually have to solve it. But we're gonna solve it right now because we're cool that way. And as a reminder, nano is 10 to the negative 9. And this time you're not squaring the denominator.
I got negative 5.08 times 10 to the negative 7.
Negative 5.08 times 10 to the negative 7th.
Yes.
Units?
Joules.
Yes, joules. Anyone else get the same thing?
Oh, there's 0.8, 0.2, and 0.7.
0.8, 0.2, 0.7.
Okay, then I got the same thing.
Okay. Questions? I was trying to stall just a little bit because there's still some people trying to get the same answer. I wasn't trying to stop you from getting the same answer, just trying to give you time if you wanted it. All right, so we've talked about why a charge would behave a certain way. So if I've got a positive charge here and I put a negative charge in, got a positive charge at some fixed location, put a negative charge here, it will be attracted. From a force point of view, it's because opposites attract like repels. From an electric field point of view, that an electric field goes away from a positive charge, and if a negative charge is put into an electric field, it goes towards the source, or away from, it goes the opposite direction, I should say. The negative charge will go the opposite direction of the electric field, so it would go that way. So two explanations of the exact same phenomenon. We can now do it, we're about to do it a third way with electric potential energy.
So, when it's negative, what does that mean for the electric?
When the potential energy is negative?
Yeah,
Generally, the negative potential energy is, stems from an attraction.
okay,
Because if you think about the potential energy formula for gravitation, assuming it's zero at an infinite distance away, that's negative G mass 1 mass 2 over R from Physics 251. So because masses are always positive, that negative sign is built in. But here, the negative sign is not built in because you're going to get that attraction if you've got opposite charges.
okay.
Yeah, a quick and dirty look at it. Again, what's more important is the change in potential energy when an object goes from one spot to another. Other questions right now? All right, so I got a positive charge here. I know that as I go in that direction, my potential energy gets smaller. So if my potential, this is say 10 joules, maybe 5 joules, 3 joules, 2 joules. That is badly worded. I suddenly merged in with the other one. So, sorry, try that one again. Got a positive charge here, I got a positive charge here. I'm going to assume that this is fixed in space. In other words, we're going to do the whole thing from the point of view of that left charge. I put a second positive charge right here, and we know it's going to be repelled because it either follows along the lines of the electric field or like charges repel. As it gets farther away, my potential energy gets smaller. I got K, Q1, Q2 over R. So as R gets bigger, my potential energy gets smaller, which means I'm losing potential energy. It's a conservative force. So where does that potential energy go?
Into the kinetic energy?
Yes. So if I put an object here at rest, it's going to gain kinetic energy when it starts to move. As it gains kinetic energy, the potential energy has to get smaller, which it does. So that explains why the charge will repel from an energy point of view. So if initial speed is 0 per second, particle moves, let's call it Q2. Q2 moves, kinetic energy increases, therefore potential energy must decrease, and so it moves to where the potential energy is smaller. Questions to hear? Now let's see if this still works. I got a positive charge here, fixed, and now I put a negative charge. This negative charge, we know from other experience, either that it feels the electric field coming from the positive charge and goes opposite the direction of the electric field, or opposite attract. Either way, it's going to go that way. In other words, R is becoming smaller. But if R becomes smaller, isn't my potential energy increasing?
If the vectors, the further apart, they're decreasing. When they get closer, wouldn't it increase, or would that vector just shrink for the radius of how?
So you're backing up what I just said, that
Yeah.
as if the negative charge gets closer to it, the potential energy will get bigger?
The potential,
It should.
If the potential energy gets bigger, then it's a conservative force. Energy is conserved. It starts at rest, so no kinetic energy. If the potential energy gets bigger, where does that come from?
so
You can't get blood from a stone.
would the potential energy stay the same until they connect?
It would not stay the same.
I was just thinking that the vector would shrink. Or I mean, the vector would stay the same until it got to it.
Yeah, well, one, we're dealing with scalars here, so
Yeah.
Since one of the charges is negative, the overall potential energy gets more negative as you get closer.
yeah, and that's the difference. -4/2 is bigger than -4/1. Because they're opposite charges, the potential energy decreases as they get closer instead of increasing. If they were the same sign charge, the potential energy would increase as you got closer, but because they're opposite signs, potential energy decreases, and that gets converted into kinetic energy. So we now have an explanation for why opposite charges will come towards each other from an energy point of view. Questions to hear, because we've got one more way of explaining the exact same thing. Other than, magic and luck. Just thinking, suppose it actually was random, that we've made rules out of things that don't exist. It's just coincidentally, every time we've tested it, it happened to fit this thing that we